Hello everyone and welcome to this last lecture of this online NPTEL course on aquatic geochemistry. It had been a wonderful journey for me to be able to talk about all the different kinds of aquatic systems and their chemistry. And in this final lecture we are going to conclude, we are going to wrap up of all the things that we had been discussing. So, we had been discussing first the first module was on global water challenges, right? And we had been talking about different problems, and I think if you remember the first problems that we discussed was how water is known as understanding of water is so important because providing clean affordable water is a sustainable development goal, that is SDG 6, and it is central to all the other sustainable development goals. Not only that, it is also central to our understanding and our mission of One Health, because we know that it is not only our health that is important, that is human health. We are all living in a very connected ecosystem, not only ecosystem, we are living on this same planet, the blue planet, and we have to be remembering that even a small act of that anthropogenic act can have very large and long term effects on the ecosystem. So, there is the One Health concept, and of course, we need to always remind ourselves that our activities has a huge impact on the biodiversity of the planet. That is rapid loss of biodiversity everywhere, not only in the oceans, there is terrestrial, different ecosystems, they are losing species at a rapid rate, and all that is either related directly to some anthropogenic activities or indirectly through climate change, which is also expedited due to anthropogenic activities. So, this connection we need to be aware of. We need to be aware of how we are modifying the global water cycle, how we are changing the global water cycle, how by modification of the global water cycle, we are fundamentally changing the global geochemical cycling of elements, and that is impacting somewhere or the other, right? That is impacting some ecosystem of the other. For instance, when we say that we are going to change more and more land cover from forest to urban areas, we are doing that. We are rapidly urbanizing everywhere in the globe. There is more growth in the number of cities, and with this urbanization there are number of problems that is coming up. Okay, a number of artificial chemical compounds are getting created, they are being sent into the ecosystem, and with this kind of new chemicals, with this kind of modified elements that is happening is that our understanding also has to rapidly evolve. Okay, how we are changing the global elemental cycles also has to evolve. I know in our lectures in river chemistry, in ocean chemistry, we understood that how these trace elements, even being so low in concentration, are so important for the ecosystem. Okay, how the biological pump depends on the micronutrients, how the biological pump can be modified if we change these elemental cycling. For what? For instance, iron, copper, zinc, they are all essential micronutrients, and they are all extremely mined for the steel industry, for our infrastructure. So, their cycling in the environment has rapidly changed. okay, their supply to the oceans has changed, okay, sediment supply to the oceans has changed. We are creating more and more dams, we are transferring, we are, you know, whatever the water was supposed to go to the ocean, we are, you know, we are saving that. With that we are changing the, you know, sediment, also not only we are changing the water, we are also changing how much sediment is being carried to. So, there is a lot of modifications that we are doing, and that is going to impact the global elemental cycle in the long run. So, now we may not be understanding the fluxes, we are still in the process of understanding how the fluxes, how to calculate the fluxes, how to constrain the elemental budget. What do I mean by elemental budget? Budgeting means we have to take into account all the sources, all the things. So, that is like budget. So, the storage is there, the input is there and the output is there. So, what is the storage in a system? The input minus the output. Okay. So, the elemental budgeting, such kind of budgeting, every, you know, every ecosystem we do it. Every, what is the net sink? If the net sink is the ocean, if we are using that ocean's data, if we know the paleo history of that particular metal in the ocean, then we do with respect to the ocean. In fact, all the budgeting is done with respect to the ocean. How much final it is there in the ocean, that is the net sink. See, we are always trying to understand how much is this delta storage varies with time in the ocean, because that gives us a proper reference, because land masses are always varying. Today what is a forest, tomorrow may be something agricultural field, another 10 years down the line it may become a city. So, land mass, you know, is always changing. So, the oceans, other, you know, the oceans are in that way pretty, they are continuing to be the way they are for a very long time. So, rapid changes in the oceans for a change to show up will take a very long time. So, that is why all the elemental budgeting is done with respect to oceans. So, how the global elemental cycles are changing, okay, that again is extremely important to understand, and very, you know, rapidly, you know, growing area of research in today's day. Every element, how it is getting mobilized through the ecosystem, through the different hydrosphere, biosphere, lithosphere, how it is getting mobilized, we understood that. Then we started looking into particular frameworks for the future. For instance, the WISER framework that was there for, you know, understanding how efficiently we can use our water. So, water related problems are various, right. So, first we need to understand what is contamination, what is quality. So, we discussed what are the quality parameters, not only the basic parameters such as pH and TDS, we have to have more understanding of the dissolved constituents. By dissolved constituents, I mean not only the major cations, the nutrients, the anions, the trace elements are also very important, and extremely important is understanding the organics also, because they severely control how it is getting, you know, mobilized, how a particular element is getting mobilized in a system. So, we understood how, you know, WISER, if we are moving in that WISER era, that means where water is more and more recycled, okay, then what are the things that we need to be aware of? Okay, where can we use the water? What kind of treatment the water needs to be, you know, done, not only for particular elements, also for emerging contaminants we need to screen. And therefore, that concept of emerging contaminants came up, where we know that we have a lot of, you know, pharmaceuticals, we have a lot of dyes, chemicals, you know, fertilizer and agricultural products. Then we had a lot of, you know, hydrocarbon products, different kinds of personal care products. So, all kinds of products that are getting into our aquatic system within a very short period of time, we have enhanced the number of such contamination. And our treatment processes have still, you know, been very rudimentary, like we still only know how to separate fluorides, how to separate arsenic, how to remove maybe a few heavy metals, but we still do not screen for a lot of personal care products, for a lot of persistent contaminants, such as different kinds of pesticides, herbicides, for certain pharmaceutical remnants which can remain in the environment for a very long time. And through the water, it's very it can get transmitted across the soil, across the rivers, across the lakes. It can get very rapidly distributed into the environment. So, understanding how this is how this is getting cycled in the environment, how it is getting transmitted through the aquatic system is very important, the emerging contaminants. And not only that, how microplastics, again an extremely important and rapidly growing area of research, how it's getting mobilized from different sources into the aquatic systems, and how long are they persisting, what are their effects on not only human health, but on all different kinds of species. Very rapidly growing area of research, and it's how it is modifying how we look into water quality therefore. So, we looked into the natural water compositions. I hope you understood how the different systems vary, rain composition versus lake river composition versus groundwater composition. We targeted particular chemical reactions. We tried to understand how thermodynamics is the most fundamental concept to understand, because the basic the basic chemistry of any aquatic system is through the weathering of different minerals, and the weathering reactions of these minerals is dependent on the thermokinetic principles, okay, which is going to get solubilized, which reactions are going to happen, how much free energy of the system is there, that controls these reactions. So, these basic weathering reactions are dependent on the thermokinetic principles. So, therefore, we try to understand how thermokinetics is important, how it works in terms of aquatic systems. Not only thermokinetics, pH, that is acids and bases, also controls the distribution of a lot of metals. So, why pH is such a master variable? It is such an important parameter that controls the chemistry of the system. So, whenever we talk of water quality, we are always trying to measure the pH of the system, because that controls the variability of a lot of other metals. So, it is not only pH, there is dissolved oxygen, with which is related to the redox reactions. So, the redox reactions, the acid bases reaction, the reactions with the aqueous complexation formation, these are all the secondary kind of reactions that will happen once the metals are there in the dissolved state. Okay. Before that, we also looked into how to sample different kinds of water, what kind of methods we should apply, what kind of preservation techniques should be there, how to select the samples, how to determine the temporal frequency. So, that was also informed in that particular module. And for different processes, for different research objectives, we need to get the data of different chemical parameters. For certain research objectives, it is important to have just a fundamental data sets of concentration of different elements. For some others, we need to know the isotope compositions as well. So, for that such kind of process oriented studies, we looked specifically into the radioactive isotopes and also the stable isotopes. So, we looked into the radioactive isotopes, the strontium isotopes and the neodymium isotopes, how their variations have informed us so much of not only the current processes, but how the strontium isotopes are also linked with paleoclimate, the carbon cycle, and our understanding of these processes that we are currently seeing with with the paleo records. So, different isotopes, they have different applications. So, the application of neodymium isotopes on the other hand to be used as a tracer of mixing in the oceans. So, it is again a paleo proxy for ocean mixing. So, the records, how they show how the ocean has behaved in the past. Not only that, we looked into a great depth on the stable isotopes of water, that is the oxygen isotopes and the hydrogen isotopes, and the kind of applications that we have for this two systems, that is the oxygen isotope system and the hydrogen isotope system, is huge. Okay, starting from understanding of the climate, like how in aquatic systems how the water isotopes simply behave, because I think all aquatic systems, they start from their start from rain, and we looked into how rain compositions vary, how the isotope compositions of rain are so different, and the processes, the kind of parameters that, so temperature, latitude, what are the controllers of the isotopic composition of rainfall. And then from rainfall, we found out the records, the ice records, how they can be used to track paleo temperature. Okay, so when were the colder regions, when were the warmer regions on the earth. Then we looked into its application in understanding the oceans. Okay, so the oceans mixing, how stable water isotopes, how they can be used to understand the processes such as that keeps the isotopic composition same. So, the diagenetic processes, the biological processes that alters the isotopic composition of oxygen, the isotopic composition of hydrogen, not that much for hydrogen, but more in terms of oxygen. So, how that gets modified due to the different processes related to natural weathering and diagenesis, and specifically magmatic processes as compared to the biological processes. So, again we learned into great depth how the fundamentals work for these radioactive isotopes as well as the stable isotope systems. And I also tried to give you particular mixing understanding, that if there is a mixing happening, how we can do the source apportionment. Okay, because that was so important, because when we are trying to understand a system, we are trying to see some signatures, we are going to have to ask these questions. Okay, where is this coming from, what are the sources, what are the sinks. So, there will be a source, there will be a sink, there will be different components that are mixing, and different isotopes can be utilized in different through geochemical modeling to target specific research questions. So, that I discussed in one particular lecture, where we discussed about mixing theory, we are discussing about how the mixing models can be how can you draw a mixing model, and how you can try to compute it through different languages. I showed you a particular specific problem from my own research, and how you can do that kind of coding using a particular language. Say suppose if you know MATLAB, if you know R, if you know Python, so you can do such coding, or you can use already built mixing models, and you can look into the interfaces. And specifically I think I showed you the interface of to do speciation calculations, that is the visual MinTech, and how when we are talking about water quality, how important is to understand the speciation aspect. So, when we report data, when we report saying that okay, so and so metal is in very high concentration, we not only have to give importance to its concentration, but we also have to give equal importance to the speciation. And specifically with speciation, how so important to understand is that not only we have inorganic species, we also have a lot of organic speciation. So, for the inorganic speciation, I showed you the visual Mintic interface, how it can be done. And for the organic speciation, there are different again geochemical models. VAM is a very well known and very utilized interface again, and if you are interested you can go back and look into it. So, we discussed on that, and then we discussed on particular traces, right. We discussed about carbon as flowing through the different aquatic systems, nitrogen as a tracer. We discussed about different metal isotopes such as iron, such as lithium, which are traces of particular weathering related activities, and iron, which can also show a lot of biological processes, and iron can also show anthropogenic modifications. And particularly for anthropogenic, we discussed the lead isotopes, and that also we tried to understand how lead is such an important and such an good tracer of aquatic systems because of its different compositions, different fingerprinting isotopic compositions in the different aquatic components. Not only that, we moved into particular problems and how the composition of particular aquatic systems vary. So, we started looking into precipitation compositions, we started looking into how the soil moisture varies. We looked into glaciers, and understanding the glaciers currently is extremely important because of the rapid transformations that is happening with the advancement or with the extreme pressure of anthropogenic activities. There is a lot of changes the globe is seeing. There is a continuous war that is happening. In the recent last 3-4 years, there was a war. Previous to that, there was a biological scenario. So, there was COVID. So, something or the other is always happening that is impacting our aquatic systems. So, either as a contaminant or either as heat in the environment, we are always modifying something. So, the glaciers which are so susceptible to such changes and how their chemistry is so important for the rivers that is flowing from these glaciers, how they are important in terms of oceans because they carry these nutrients. And as I showed you in the ocean composition lecture, that the sediments and the nutrients that they supply, they sustain a lot of life in these regions. So, it is very important to understand glacier biogeochemistry and how different aquatic systems are dependent on the glaciers, specifically the rivers and the groundwater. Not only the rivers, the groundwater is also equally dependent, specifically in the mountainous regions where the rain supply is very limited and very seasonal, and it is the snow melt water and the glacier melt water which can be the recharge, which is the main recharge. So, this groundwater, the rivers, they are the sustaining the people who are living there, and these are the people who are also subjected to the maximum amount of threats from climate change. So, if there is certain if you look at the prone like which people are more prone, to impacts of climate change, you will see that the people who are living in the mountainous regions, they are more susceptible to impacts from climate adversaries like some kind of hazards or just simply the lack of water. So, if you just remove the glaciers, then what will happen in this area? So, we always have to think about the future. We have to think about how sustainable our activities are, and how sustainable will how sustainable will the water resources be in the future for our water security, for food security. So, all that is related to the glaciers, specifically in the Southeast Asia, because of the large number of rivers that are dependent on the glaciers. Then we looked specifically on river chemistry, because we know that rivers, they are the primary they are the primary source of water for many regions. Okay, they supply the water required for agriculture. Many regions, they depend on the rivers directly for their drinking water, and the industries, they depend on it. So, not only that, they are also subjugated as the waste conducts. Okay, so they also are the waste conduits. They will accept all the waste. Now, all the streams, they are so effluent dominated. So, it is very important to understand our rivers and the river chemistry, which is so subjected to anthropogenic modifications because of all the projects that we are doing. We are having more rapid agriculture. There is so much of water abstraction that is going on. There is so much of addition of effluents to the river systems. We are modifying the volume of water that is passing through. Therefore, we are changing the rejuvenation power of the river. So, that kind of understanding is required. We looked into the chemistry, and we looked into the water quality parameters that is that controls the importance of understanding reactive transport of metals in rivers, because it is not only just source and sinks, there is rapid transformation of metals in the river itself. So, we need to understand that when we report a particular river, and we need to also understand, that is, we need to compare our rivers with the river itself. We cannot compare it always with the with the drinking water quality. So, there is always a background value that needs to be investigated, needs to be there. Then we looked into groundwater. We looked into specifically groundwater issues with salinization, with the contamination with particular geogenic contaminants such as arsenic, such as uranium, how different areas over the globe, due to natural processes and human human mediated processes, we have modified the mobilization of particular metals in the aquifers. Understanding it is so important, because all our water related challenges are related, because groundwater is the most stable supply, and India is the largest consumer of groundwater in the world. We actually consume 1/3 of the entire groundwater in the world. So, understanding groundwater, its composition, how particular regions are seeing some problems. If we see the problems, how to target those issues, specifically with fluoride contamination, arsenic contamination, uranium contamination. So, these are natural contaminants that are there, but certain times they are mostly modified due to our activities, such as we have a lot of wells digged, we are changing the aquifer parameters, we are changing the aquifer characteristics. So, we are changing the recharge, we are rapidly drawing out the water. So, that kind of changes, and of course, we looked into lakes as well. We looked into a specific problem related to eutrophication and what kind of modifications are required, what kind of steps are required if we need to control that. and we thereafter we ended with the module with seawater composition, and I talked about the different expeditions and specific results that came out especially from the GeoTraces program. And with this, I hope I gave you an understanding of the natural aquatic systems and how the chemistry is so variable and variable due to different causes. Okay, starting from natural causes such as weathering to human, human related, and how all our water challenges are all linked to the things that we have done, we are doing currently, or we have done in the past. So, when we are looking into a water issue, we have to understand that even if for a particular element there can be many processes involved. We not only look into the inorganic processes, we also look into the organic processes, and we definitely try to work it in the best way possible, using a lot of ground data, using a lot of modeling, understanding it from the critical zone point of view for the advancement of science, and that I think will be able to help a lot of challenges and also be useful for the sustainable water supply and its maintain its integrity as a as a system. So, there are laws, there are things that identifies aquatic systems as having particular rights for themselves, but scientists and specifically students and researchers, I hope we all understand that these are very interlinked systems, and our understanding has to move rapidly because our challenges with these systems are growing rapidly. So, research in these areas has to rapidly increase to keep up the pace of the challenges with our solutions. So, I will be ending this course and saying that our future is dependent on what we do and specifically related to water. And I hope all of you have learned something through this course, and if you have any questions, please feel free to write down in the NPTEL questions sessions and the sections if you have particular questions and any doubts related to any of the lectures. I will be very happy to answer your doubts, your questions. I hope you will be knowing about the exams and all that from the NPTEL system itself. Otherwise, any question you can directly write into the NPTEL platform, and I will be answering your doubts. And there will be a specific session, a video session where you can directly join and we can have a live discussion. So, thank you. With that, it was very good to have this course and share all the information with all of you. Thank you very much for registering for this course, and I hope you have enjoyed and learned something about aquatic chemistry. Many portions were not could be done completely. They are all different topics. For instance, the chemical oceanography itself is a very vast subject. Many tracers also I could not discuss because I have to discuss a lot of things in this course. So, if you feel that certain things were not well discussed, I think I have left you with enough references that you can go back and look into it, and you can let me know of any more knowledge, any reference that you could not find. So, with that, thank you and all the best for the exams. Thank you.